Okay, so I'm going to give a quick summary of all these terms that deal with basically the major concepts in this chapter. I'm going to try to keep it quick, simple, not be very detailed. So this will be something that's going to be helpful if you're cramming during those last 5 minutes right before a test. So really watch and listen carefully as we go over this. So first thing you have to know in this chapter are the basic terms when we're saying relative extrema, relative maximum, local maximum, local minimum, absolute maximum, absolute minimum. So what we're talking about are what you would think when we say maximum minimum. We're talking about the biggest, largest values or the smallest, lowest values on the graph. So you can see on this graph, you have, low values here, here, and here, and the high values here, here, and here. Now, when we say absolute maximum or absolute minimum, we're talking about the biggest value on the closed interval. So if we're going from -5 to 21, this would be our absolute maximum over here. Or we can just say absolute max for short, because that's bigger than all the rest. Over here, this would be our absolute minimum. Absolute minimum, if I keep it short. Now, the other ones we call this like a local max. This one over here would also be like a local max. This would be a local minimum. Local min. It would also then be a local. Okay, so then what we want to next understand is how the derivative relates to local maximum or local minimums. So what you're going to notice is that at all of these values, you're going to have a horizontal tangent line. You're going to have a line, sideways if you regard a derivative. A horizontal tangent line here, horizontal tangent line here, horizontal tangent line here, and a horizontal tangent line here. We're not going to have them at the end ones because obviously the graph stops. But within, these, we have that f prime is equal to 0 at x equals 0, 10, 15, 20, and also over here, it's kind of hard to see, but also at 5. So f prime of x equals 0 when x is 0, 5, 10, 15, 20. So like how does this help? Well, this leads to critical values. You're going to have critical values over here. These are also known as the critical values. When you were trying to figure out, how would you figure out where the extreme values would be if you're not given the picture of the graph? You're going to be given equations in your class. You're not going to be given the picture. That'd be way too easy. Way too easy. So your teacher's going to give you equations and they're going to tell you, find the maximum, find the minimum. Where are they in this equation? So what you want to do is find the derivative of the equation and find where the derivative is equal to 0. And you can see why, because whenever it's equal to 0, you can have a potential local minimum or maximum. Or maybe something weird occurs, but you still want to study it. So you want to find where the minimum, where the derivative is 0 or where it's undefined. We call those critical values. Now, what does the first derivative test say? This tells you that you can find if it's a maximum or minimum at these extremas if you can determine what the first derivative of the function is doing before and after them. So what you're going to see is that on here, on this part right here, on this region, and on this region, here to here, and on this region, that the function is increasing. It's getting larger, obviously, right? But what does that say about the first derivative? Well, the first derivative is positive. The first derivative is positive on those intervals. The first derivative is positive on -5, 0, 10, 15, and 20, 25. So we want to see where the first derivative is positive, and then we also want to see where it's negative, because you can see that between here, we're going down this path, the function is decreasing. I'm not going to trace that perfectly, but all right. It's decreasing, it's negative here, and the function is decreasing. So the first derivative is negative on those intervals. So it's negative on 0 to 10, and then from 15 to 20. So that's what the first derivative test is telling you. Study what the first derivative is doing on intervals between critical values, and I'll let you see or figure out if you have local minimums or maximums at those extremas. If you don't have a picture, obviously. If you have a picture, it's easy. If you don't, you got to figure out another way to do it with equations and such. Now, what is the second derivative test? Well, the second derivative test actually basically connects to also what's called concavity. So let's look at both of those. So what that is saying is that when you have the concavity of a graph, meaning like the way it's like I don't know how to say it other than the way it's concave down or concave up. So let me just put it another. Let's draw that up. Powerful. On this region right here on this interval, and on this interval to here to here, we have it's concave down on those two parts. Just looking at the shape, it's also concave down here. So we can say concave down on -5 to 3, 5 to 7, and then 13 to 18. 13 to 18, it's also concave down. Now, when it's concave down, like what does that do with the second derivative? That also means that the second derivative is negative. Second derivative is also negative on those intervals. That's when it's concave down. So you can find where it's concave down by finding where the second derivative is equal to is less than 0, and it's going to essentially be like I don't know how to say it, so it's going to be like an upside down parabola. That's how I'll say it, like a decreasing parabola sort of thing. Now the opposite of that is when it's concave up. So it's on concave up here, and concave up on the rest. So when it's concave up, the second derivative is positive. So then we could say concave up on 3 to 5, 7 to 13, and then 18 to 25. And that's also going to be when the second derivative is positive. That's when greater than 0. And think about it, it's greater than 0 or positive when the first derivative is increasing. That means when the first derivative is getting larger, the second derivative is positive. And when the second derivative is negative, if the first derivative is decreasing, it's getting smaller. Now, inflection points are just going to be where the graph changes from concave up to concave down. So you would have inflection points over here, and an inflection point here. We call it IF or IP, inflection point there. An inflection point over here as well. An inflection point over here. I got several. We have another inflection point here. Another one here. So we got 1, 2, 3, 4, 5 inflection points. 5 inflection points because it's changing concave down to concave up to concave down, concave down to concave up, concave up to concave down, concave down to concave up. So that's what an inflection point is. And at those points, you're going to notice that you're going to have either a vertical tangent line or a horizontal tangent line. You're going to have an undefined tangent line. So that's how you can figure out where the possible inflection points are. But what you would look is where the second derivative could also be equal to 0. That's another way to find it. Second derivative will just say it's not that it's guaranteed to be 0, but that's one way you can determine it. So use all those together, and logically, it all makes sense, and you'll be able to figure out any graph as long as you do the algebra and the derivative calculating, and you'll be good.